Hello everyone, I am Osman Nur Başural. I am a physics student at Bilkent University. Today I will talk about my physics experiment about energy, force and oscillations in a spring mass system. In this experiment, I looked at how energy changes from one form to another, how spring stretches when we add weight, and how its stiffness and the weight affect its movement. The goal of the experiment was to figure out the spring constant of an unknown spring. Check if the results match theory and see how different weights affect how the spring moves back and forth. I did the experiment in three parts. In the first part, I compressed the spring 2 centimeters, 3 centimeters, and 4 centimeters. Then I released the springs. Then I calculated the spring constant by using equation 6. Spring constant was 130 for the 2 centimeter compression and the 3 centimeter compression, but spring constant was 120 for the 4 centimeter compression. So we can say average spring constant was 126.7. I couldn't calculate the error percentage because I started with a spring that constants are not known. However, I tried to decrease the error by using an error table, which helps conserve mechanical energy by minimizing drag forces. I measured the same data many times and took average of them to escape errors. The second part, I added the weights to the spring, measured how much it stretched and compared to the result to what theory says. First, I measured the equilibrium length of the spring. Then I added one mass and measured how much it stretched. I did this 3 times to get a more precise result. And it stretched about 30 millimeters. Then I had one different mass and measured how much it stretched. I did this 3 times again. But now the springs stretch about 53 millimeters. Doing so, I could calculate the force exerted on the spring by using Hooke's law, which says force on the springs equals spring constant times compression distance. In addition, this value must be same as the weight of the masses, because in the max length, mass has no acceleration. Hence, by Newton's second laws, which says force equals mass times acceleration, the net force on the masses must be zero. When I bend mass 1, I calculate the force exerted on the spring 2.5, which must be theoretically 2.6. And then when I bend mass 2, I calculated the force exerted on the spring 6.66, which must be theoretically 7.65. The error percentage for mass 1 was 10.1%, and for mass 2 is 13.7%. The errors show I could not determine the accurate spring constant. The reason behind the error could be human mistakes and the materials that I used to measure time and distance. Additionally, if we calculate the spring constant theoretically by assuming the stretch length and the mass is measured correctly, we will find the spring constant approximately 145 Newton over meter, which is not same as the I found in the first part. In the third part, I attached the weights to the spring, pulled them down, and the time how long it took for them to go up and down once. I compared this time to the theory. For the mass 1, the experimental period was 0.309 seconds, while the theoretical period was 0.365 seconds. For the mass 2, the experimental period was 0.365 seconds, while the theoretical period is 0.465 seconds. The error for mass 1 is similar to the errors that I found the earlier parts. However, the error that I found in mass 2 is greater than the other values. The higher error for mass 2 could be attributed to difficulty in controlling its path. Since mass 2 is heavier than mass 1, it was harder to achieve a smooth motion when released. In conclusion, this experiment focused on studying how a spring behaves when compressed or stretched. We calculated the spring constant using energy conservation, tested it with weights to see how accurately each matched theory, and observed how different weights affected the time of oscillations. The result shows the relationship between force, displacement, and the motion, and how they align with theoretical predictions. Despite the similars, the experiment successfully demonstrated the key principle of physics related to spring systems.